we have here Pooja Malik with me. She led our GPU efforts in Sedai. GPU spend is out of control. Most teams do not have an answer. A survey says if you have one GPU wasted at, say, 30%, that's going to cost you 70K a year. There are three hard problems to solve this task in front of you. Number one, the measurement. Second is execution of optimization. The third problem is how to execute these optimizations dynamically and autonomously. I'm Suresh Mathew. This is One Idea. Welcome, Pooja, to the show.
Happy to be here.
So, Pooja, let's talk about the first problem statement. Two unsolved problems. We'll talk about the first one first. What was the difficulty in this measuring metrics, finding out the usage precisely, and what was the hardest or the difficulty there?
There are two layers to this problem. The first one being coming from infrastructure background. The first thing you see for most of these products is utilization. nvidia-smi, you hit in nvidia-smi, you try to see GPU utilization, and what you see 95% utilization. You check the logs, there are no errors, and you think that we have got it, everything's going good, great. But you realize that you're using really a fraction of GPU.
Basically, the workload is so small, but it's really occupying the whole GPU.
Basically, this number means it's meaningless.
It's misleading.
It's misleading. That was our approach, that, actually deducing what this number means and how we can come up with the actual GPU utilization.
So basically, this number, even if the number says 100%, what you're telling me is you cannot trust that number.
Right.
Your GPU could go further and utilize even better.
Right.
So when it's showing 100%, it is not really at 100.
Yes.
Okay, I see.
And the second point was, so even if you understand that this is inefficient, then you get into another problem, which is the complexity trap. So there is no single metric to say how efficient your GPU is. So you have to decide based on memory bandwidth or SM efficiencies or occupancies or kernel efficiencies to really come up with a picture. And even then the picture is still murky. You don't really have the exact numbers. It's a well-known fact, and as you mentioned, that most of the well-optimized GPU workloads cannot really use more than 30 to 40% of what GPU is capable of.
It's not just one number, it's multiple numbers.
Right.
So is this combination as just one combination, or is it a trend in play too?
So there are places where you are trying to basically copy data. There are places where we already know that this copying data will be slow, and there is trends too. Like the usage in, for example, let's say a training workload is completely different from an inference workload. It's completely different, for example, from a batch workload.
So it's a combination of metrics. So now let me start with the basics here. So what exactly is the difference between a CPU and a GPU? For those who are not very familiar with it, what is the difference?
So CPU is basically is a set of powerful cores. Powerful intelligent cores. Some might have 8, 16 or 32 cores or 64 cores depending on the chips. It's basically a kind of a generalist. You have specific jobs to do, whatever. Memory bandwidth placement, or some multitasking, or some kind of decision making. So what makes software work is what CPU is capable of doing.
So CPU is really getting an instruction, making sure that it's executed right, and it's smart enough to execute it right. Okay, now what is GPU?
So GPU completely changes the model. So GPU is not that intelligent, but it is fast as an aggregate. So you basically give GPU the task which you want to be done, the same job can at a fast pace.
So it has multiple swim lanes.
Right. So the best analogy that I usually use for CPU and GPUs is that consider CPUs as a team of chefs who can create different dishes for you.
Okay.
And GPU is basically a line of chefs who will get your onions chopped. But if you want some, a 5-course meal to be formulated, you use CPU. But the catch here is you cannot use one without the other. So CPUs is what innovates, and GPUs is what executes. Yes.
That's the controller. That's a smart module. And GP can execute in multiple swim lanes. Okay. Memory is one of the things that shows up in most of our optimization or wastage discussions, right? Why is it more important here in the case of GPU and not so important in CPUs?
The basic thing is that in case of GPUs, it is actually a bottleneck. In CPUs, it's very simple that you have a system RAM, and that system RAM, the CPU that can directly access that RAM. And in case of GPUs, you have a VRAM, which is part of that physical card. So now what happens is you have two memory pools, and both CPU memory pool and GPU memory pool has to talk to each other. They have to transfer data to each other, and that is done using something called a PCI link, which is the slowest thing. In my opinion, most of the people talk a lot about spending money on flops or the compute specs, but the memory transfer and waiting for the memory transfer is one of the single point where we have a lot of data.
That's a true point.
Yes.
I see. So is there a metric to identify these?
So not just one. Again, there are multiple metrics that you look at.
That's the challenge there. Okay, I see. When you set out to build the optimization monitoring algorithm at Sedai, right? How did you get started? What was your approach to solve this?
So once we realized that the GPU metrics is misleading, and if you are from the CUDA background, the first thing that you do is actually check the hardware, and you write programs to validate it. So what we did was, or what you should do, or what anyone else should do, is you basically you start simple. You write a CUDA program, which is just in interacting with one SM, has one thread, just interacting with one SM, and that's when you see how the metrics behave.
And for those of you who do not know what SMS, it is
Streaming multiprocess. And then you complicate things. You try to give it a little compute heavy or a memory heavy workload. You try to experiment with it a little bit, and then you see patterns. And it's basically like you see fingerprint kind of thing, where you see, okay, under how a compute heavy workload behaves versus how a memory heavy workload behave under what kind of compute, under what kind of GPUs, under what kind of situations and conditions. So you get that fingerprint, and that's basically how our algorithm came up to. And then we also experimented with actually the real workloads.
And what language do you use to write these?
So you can write both C++ to write CUDA.
Let me make sure that I understood this, right? So you start writing a kernel module. You figure out how exactly is that module reporting the metrics. You look at the metric trends. You start teaching your model, you know what, these are the things I should learn. You now have a combination that works. And you also have a fingerprint that tells you this is the time you should take an action. So basically, you have to start interacting with your GPU really deeply without scratching the surface. So reading is not the solution here. Trying is a solution. Is that right?
Absolutely.
So basically, you have all the metrics now. You have metrics changing. You now know the list. What you do not know is, what does this mean? And these experiments will help you figure out what's the deal. Okay. Now that you have the algo in place and you have a model that can tell you a lot of things, the next thing is to validate and what you got is right. Right? There has to be some correctness check. Yes, you got a solution. We are all excited. Now, how do you know that it's right?
So frankly, that was one of the hardest problems because there's no industry standard right now. It's very new. Nvidia doesn't publish any industry standard, and what works for one kind of workload might not work for the other.
Give me the kinds of workloads.
There can be LLMs, which are training workloads. There can be inference. There can be batch.
I see. So training and inference could be two different types. Okay, got it.
So the reality is that there is no industry standard. So what you do is you build your own. So what we did was we for each application we almost came up with a model, and based on that, so basically we observed patterns. How when the application looks good, when the application looks bad, when what are the early warning signs, and based on that model is how we created our algorithm and how we validated things. The other very important part is the feedback loop. So how Sedai generally works is whenever it identifies a issue, it fixes the issue, and then it feeds it back to the system.
I
So
see.
the system learns from itself.
So basically, you see a problem or an inefficiency, you figure out what the problem is, you go fix it, then you learn from it. So you can do it better the next time. You don't have to go through the cycle again. Okay, got it. When you looked at all the metrics available, is there a metric that I should stay away from?
GPU utilization.
So basically, you're trying to increase GPU utilization and you did not look at GPU utilization metric. Okay, that's interesting. Now let's get into the second unsolved problem. So we talked about the first one, which is identifying the metric and figuring out the model and the algorithm to see or confirm the inefficiencies. So let's now talk about the second problem statement, which is how to increase the efficiency or how to fix the inefficiency. I know there are a few options there. At least I've heard of a few. One is, I'm thinking DRA. The second would be maybe time slicing. The third I'm thinking would be some cloud providers do provide a higher abstracted time slicing as well. Now, how did you go about solving this?
So actually, this is the most interesting part, and also the most frustrating part, because the tools have not reached that because it's newer. The tools are not there yet. So time slicing is basically that only your time is divided. There's no isolation.
So you use the same GPU, land the workload, and time slice between workloads.
Right. So since there's no isolation, you cannot really use it in production. It's possible one compute heavy workload might interfere and take all the resources and everything. So the second is MIG. So MIG is promising. In theory, it's basically distributing one full GPU, one full physical GPU into smaller chunks, into smaller slices. So in theory, it looks very good. But in practice, you have to it's basically like decide. It's pre-decided. You have to choose from a pre-decided menu of slices. So you really cannot say that I need 37% of your GPU. That's not there. But so most of the people are okay with they make it work.
So you have predefined slices. You pick one of those. Is that what you're saying?
Correct. And then comes the DRA. So DRA is a layer on top of MIG, which is called this dynamic resource allocation.
Which is a Kubernetes construct.
Right. And the DRA is basically, it is helping us with scheduling. So it's basically it helps with pre-deciding or it helps with deciding which chunks,
which you have already predefined. So basically, you have divided your GPUs into multiple slices, and DRI will help pick one.
Right. So it helps with the demand shifts.
Got it. So that's a complete solution in my mind, except for the inefficiencies in each of these ways.
So the problem is DRA is there. It's almost there, but it's still not production ready. Like we are still in the early stages of adopting DRA. So we are hoping that it gets into production soon.
Now about the AWS or cloud providers generally giving you that feature with things like fractional GPUs. Are you guys looking at that too?
Yes. So we do have support for fractional GPUs also, and it was like exciting that no, we don't have to do MIG at our end, and cloud provider itself are providing it, but only right now only AWS is providing the fractional GPUs, and it's basically again a very similar concept as MIG. The only difference is they are actually not doing MIG. They are using a hypervisor to divide the GPUs. Memory is completely isolated, but GPUs, the compute is basically divided as time sliced.
So you support MIG, you support DRA, and now you support fractional GPUs too. Okay, got it, clear. Pooja, I want to know what are the mistakes you made when building this capability for Sedai?
So I would say, one thing was GPUs seem very intimidating, being the big architecture and the complicated architecture. So it was a little intimidating in the beginning. So the mistakes that we did would probably be, just again, as I mentioned earlier, it was GPU utilization. GPU utilization was not giving us the numbers that we expect. It was not making sense at all. And initially we went with, using GPU utilization.
I see. Okay. So basically, you saw, or one of us saw GPU utilization, and we thought that is going to give us the answer. And probably we wrote code against it too, I'm assuming.
Yes.
And then realize that it's not giving you the right metric. And it's not even slightly wrong, it's completely wrong. So basically, a word, GPU utilization, that metric, the metric with the name GPU utilization itself was not giving you the utilization the right way.
Right. So it basically is saying that lights were on. It's basically just a yes or a no question, which it answers as percentage. It's not really telling, like CPU utilization, what is the actual utilization.
You see, it's not really telling you that this is a percentage or I'm utilized this much, give me more. It is like, I cannot take anymore. And this happened when you still were writing the kernel, or it happened when you were trying to, or your team was trying to read and do things.
So it happened with documentation. Their documentation is very weak.
It's not wrong, it's vague.
Yes.
It's misleading. Are you guys planning to like make any of these things documented and publicly available?
Not at the moment.
Okay, I see. So now that we have solved this problem, Pooja, tell me, what is the unsolved problem now? What is keeping you up at night? What are you going to solve next?
So I would say the GPU, making the GPU partitions dynamic. Right now they are static. So making those dynamic. Obviously, right, the traffic at 12 noon or doesn't is different from traffic at 2 a.m. So you have to make sure that those MIGs are able to, the way we do it in CPUs, the MIGs are able to expand or reduce based on the traffic need.
Like a container.
Again, that's the dream project, or that's the dream product, but and then the research is going there, but it's not production ready.
So you are expecting GPUs to be available to, say, a Kubernetes cluster and a scheduler. And scheduler can then decide how much do I want to give this workload. I'm sure Sedai will give conditions and configuration, so it makes the right choice. Then at runtime, it can then pick a slice that it wants. Is that right?
Correct.
Got it. It is exciting. Good luck with the release. And guys, this is Suresh Mathew again. One idea. If you like what you heard so far, please like, subscribe, and share with a fellow engineer. Generally, in this channel, we talk to engineers, we discuss idea, and the idea does not have to be a success. We celebrate both success and failures. So please join me and comment below if you have a great idea. Thank you.